Imagine writing a perfectly grammatical, uh, beautifully structured, highly complex sentence, and then because you missed a single solitary semicolon, a multi-million-dollar corporate server just completely crashes to a halt.
Oh, yeah, it happens all the time. Welcome to the completely unforgiving, hyper-literal world of programming.
Right. And you sit down at your computer, you have this incredible idea for an application, but the exact moment you try to actually write it out, you just hit a massive wall.
It's so frustrating. It feels less like learning a new skill and more like trying to negotiate a peace treaty in an alien language, honestly.
Yes, exactly. Suddenly you are drowning in these dry textbooks, archaic syntax rules, and exams that seem specifically designed to trick you rather than, test your actual knowledge.
Well, it was an incredibly jarring transition for the human brain. I mean, we spend our entire lives communicating with nuance and context. We use intuition. We imply things constantly.
Right, like if I ask you to pass the salt, I don't give you coordinates.
Exactly. I don't need to specify the exact angle of your elbow or the velocity at which your hand should travel. You just pass the salt. But when you step into the realm of programming, you are moving into a world that demands absolute, unyielding, microscopic precision.
It's intense.
For anyone just starting out, that shift doesn't just feel difficult, it actually feels aggressively unnatural.
I totally get that. And whether you are actively cramming for an IT exam right this very second, or maybe you are a manager trying to understand what your software development team actually does all day, or you're just insanely curious about how the digital architecture of our world functions, this deep dive is definitely for you.
Absolutely.
Because our mission today is to deconstruct the absolute foundations of programming logic and scripting. We're going to merge two very different perspectives here. First, we have the academic theory from Joyce Farrell's comprehensive textbook, Programming Logic and Design.
It's a classic for a reason. And second, we are pairing that academic foundation with the raw, battle-tested survival advice from students on Reddit.
Right, specifically the students who are currently fighting their way through the Western Governors University D278 course,
Yeah, the Scripting and Programming Foundations course.
which is notoriously tricky. The Reddit students really highlight a massive gap between the pristine theory of a textbook and the messy reality of actually passing a certification exam.
Oh, for sure. The textbook shows you a perfect world, but the students in the trenches, they tell you what mental models you actually have to build to survive the test and use these concepts in the real world.
So we are going to act as your ultimate shortcut to programming literacy today. We're prioritizing deep conceptual understanding over just, rote memorization.
Because memorizing a block of code, well, it won't help you at all if you don't understand the environment where that code actually has to live and execute.
That makes total sense. So before we can talk about writing software, we have to look at the physical and virtual canvas we are painting on.
Right, which requires a really firm grasp on the anatomy of a computer system, starting with the most fundamental divide in all of computing.
Hardware versus software.
Exactly.
It's like the classic mind-body problem, just fly to machines. The hardware is the body. It's the physical equipment, the tangible devices.
Stuff you can drop on your foot.
Yeah, exactly. The keyboard under your fingertips, the mouse, the monitor, the speakers, the central processing unit, the CPU and the memory chips clicking into the motherboard. It has mass. You can physically touch it.
But hardware on its own, I mean, no matter how much silicon or gold is packed into it, is essentially just a very expensive, highly engineered paperweight if it doesn't have instructions.
Right, a really heavy paperweight.
It possesses the capacity for action, but no will to act. And that is exactly where software comes in.
So software is the mind of the system.
Precisely. It consists of the precise computer instructions that tell the physical hardware what to do, when to do it, and how to do it. And Farrell's text breaks this software down into two distinct categories that are really crucial to differentiate.
Which are application software and system software, right?
Got it.
Okay, so if I'm understanding the terminology correctly, application software refers to the tools that I, as a human user, actually interact with to accomplish a specific task. I am applying the software to my life.
That's a great way to think about it.
So this would be like a word processor, a spreadsheet, an inventory tracker, or even just a video game.
Correct. Those applications are built to solve a user's problem or provide a service directly to the user. System software, on the other hand, operates almost entirely behind the scenes.
Like the man behind the curtain.
Yeah, exactly. These are the programs that manage the computer hardware itself, the most prominent example being your operating system.
like Windows or Linux or Mac OS.
Right. The user doesn't strictly interact with the operating system to, say, write a novel. The operating system manages the memory, it manages the hard drive, and the CPU. It creates a stable environment so that your word processing application can function without crashing the whole machine.
I see. But regardless of whether we are talking about a massive, complex operating system or a tiny little mobile application, the underlying architecture of what they're doing with the hardware is always the same.
Always.
They are always performing three major operations: input, processing, and output. I've heard it called the holy trinity of computing.
It really is. It always boils down to those three. Input is the act of getting data into the system. And we need to pause here because the textbook makes a very deliberate, vital distinction between the terms data and information.
Oh, really? Because in casual conversation, I feel like we use them interchangeably all the time.
We do, but in programming, they're entirely different states of being. Data refers to the raw, completely unprocessed facts that enter the system. A list of random names, a column of numbers, the raw keystrokes you type.
It's just raw material.
Exactly. Then comes the second phase, processing. This is where the CPU takes that raw material and does the actual heavy lifting.
Okay, what does that look like?
Well, it organizes the data, sorts it, checks it for logical consistency, or performs mathematical calculations on it. Processing is essentially the act of transformation.
And once that raw data has been transformed into something meaningful and useful to a human being, it enters the third phase, right? Output.
Yes. And at this point, the processed data is officially reclassified as information.
Okay, let me try to ground this in a real-world scenario to make sure I'm following. Let's say I run a business. My raw data going in the input would be the number of hours my employee worked this week, let's say 40, and their hourly wage, say $20. It's just two disparate numbers.
Right, just raw facts.
Then the processing is the CPU multiplying 40 by 20 and maybe calculating taxes. And the output, the information, is the finalized printed paycheck of $800 minus deductions, which actually means something to my employee.
That is the perfect encapsulation of the cycle. Raw data in, processing in the middle, contextualized information out. But there is a fourth, often silent partner in this operation, and that is storage. The computer has to put this data somewhere while it's working on it. And this is where we really need to clearly separate volatile memory from non-volatile storage.
Okay, volatile memory being RAM, random access memory. Now, volatile in a human context usually implies explosive or unpredictable, like a volatile personality.
Yeah.
But in computer architecture, we're talking about state retention, right?
Exactly. Your RAM isn't going to explode on your desk.
That's a relief.
Volatile memory simply means its contents are completely dependent on a constant flow of electricity. The millisecond the computer is turned off, or, if you lose power in a thunderstorm, everything held in RAM is instantly and permanently wiped clean.
Oh, wow, instantly.
Instantly. It is temporary, highly active internal storage. When a program is actively running, the CPU is pulling instructions and data directly from RAM because RAM is incredibly blindingly fast.
But because it forgets everything the moment the power drops, we obviously can't store our operating system or our precious family photos in RAM. We need non-volatile storage.
Which is your hard drive, your solid-state drive, or even a USB flash drive. Non-volatile storage is permanent. The magnetic or electrical states remain persistent even when the power is entirely cut from the wall.
Okay, this raises a structural question for me about how the machine actually works. If I want to run a program, the computer has to find it on the permanent non-volatile hard drive, pull it out, and load a copy of it into the temporary volatile RAM.
Right.
Why bother with the extra step? Why not just execute the code straight off the hard drive and completely skip the middleman?
It entirely comes down to the physics of speed. The CPU, the brain of the computer, operates at billions of cycles per second. It is ravenously hungry for data. Hard drives, even the most modern, cutting-edge, solid-state drives, are astronomically slower than the CPU.
Really? Even the new ones?
Even the new ones.
Yeah.
If the processor had to wait for the hard drive to deliver every single instruction line by line, the entire system would experience a massive bottleneck. The computer would just grind to a halt.
Okay, so RAM acts as a staging area. It's like, okay, imagine a master chef cooking a complicated meal. The hard drive is the grocery store down the street. It holds everything, but driving there takes time.
Right.
RAM is the chef's cutting board. You go to the store once, bring all the ingredients back, put them on the cutting board right in front of you, and then you can chop and cook at lightning speed.
That is a phenomenal analogy. That is exactly how computer architecture functions. The RAM holds the ingredients so the CPU can cook without waiting around. Now, keeping that architecture in mind, we have to tackle the language barrier.
A language barrier, right.
How do we, as humans, actually write the instructions that go into RAM and tell the CPU what to do?
Because humans write what is called source code. We use programming languages like Java, C# or Python. These languages have very strict grammar rules, but they use alphanumeric characters. They use English words like if, else, while, and print.
But the CPU does not speak English, and it definitely does not speak Python. At a microscopic level, a CPU is just a collection of billions of microscopic electrical transistors that can only exist in one of two states, on or off, high voltage or low voltage, 1 or 0.
So the only language the hardware actually understands is object code, which is raw machine language, binary code.
Exactly.
So if I am typing English words on a keyboard and the CPU only reads ones and zeros, we have a fundamental communication failure there. There has to be a translator bridging that gap.
And there is. Farrell's text details two distinct types of translators, compilers and interpreters. And I should note, this is a massive focus point for the Reddit students in the WGU course. They specifically advise studying the nuances of compiled versus interpreted languages for the exam.
Okay, so what is the core difference?
Well, both a compiler and an interpreter serve the exact same overarching purpose. They take your human-readable source code and translate it into machine-readable object code. The critical difference lies in when and how they perform that translation.
Okay, walk me through a compiler first.
A compiler takes your entire program, every single line of code you wrote, and translates it all at once, in one big batch, before the program is ever allowed to run. It scans the whole document, creates a separate, standalone, executable file of machine code, and then you run that new file.
Well, an interpreter operates in real time, right?
Yes. It translates the code, line by line, instruction by instruction, while the program is actively running. It reads line 1, translates it, executes it, reads line 2, translates it, executes it.
To put an analogy to this, let's say I wrote an incredible 500-page novel in English, but it needs to be read by an audience that only speaks Japanese.
Okay, I like where this is going.
If I use a compiler, that is like hiring a professional translator to take my manuscript into a locked room for a month. They translate the entire book, print a bound Japanese edition, and hand it to the reader. The reader gets the whole finished product at once.
A perfect parallel. The translation process takes a long time up front, but once the Japanese book is printed, the reader can read it as fast as they want. The execution is incredibly fast.
But if I use an interpreter, that would be like me standing on a stage in Tokyo, reading my English book out loud, one sentence at a time, with a live United Nations translator standing right next to me. I say a sentence in English, the translator speaks it in Japanese, the audience reacts, I read the next sentence, they translate it.
And you can immediately see the performance trade-offs in that scenario. The live interpreter allows you to start the presentation immediately, no waiting a month for a printed book.
Right.
But the overall process of getting through the book is much slower because the audience has to wait for the translation to happen after every single sentence.
Now, the Reddit students also brought up another layer to this translation process that often appears on exams. They talked about the difference between statically typed languages and dynamically typed languages. How does that factor into the compiler versus interpreter debate?
It's heavily intertwined, actually. In programming, a type refers to what kind of data a variable is holding. Is it a whole number? Is it text? Is it a decimal? In a statically typed language, which is usually compiled, like Java or C++, you have to explicitly tell the computer, hey, this variable will only ever hold a whole number.
So you lock it in.
Yes, you lock it in. And the compiler checks all of those rules before the program ever runs. If you try to put a word into a number box, the compiler just stops and says, error, I won't translate this.
It's rigid. It enforces the rules completely up front.
Very rigid. Dynamically typed languages, on the other hand, which are often interpreted like Python or JavaScript, they are much more flexible. You don't have to declare the data type up front.
So the interpreter just sort of figures it out on the fly as the program runs.
Exactly. It's much faster for the programmer to write, but it's computationally heavier during runtime. Because the interpreter is constantly checking, wait, is this a number or a word? While it's also trying to translate the code.
Wow, okay. This compiler, or interpreter, regardless of how it functions, acts as an incredibly strict, unforgiving grammarian. Which kind of brings us to a major pivot in how we think about programming. The translator's going to catch your typos.
Oh, absolutely.
If you misspell print as print without the I, the compiler will flag a syntax error.
Yes, syntax refers to the strict rules governing word usage, punctuation, and structure in a given programming language. A syntax error is simply a grammatical mistake. You forgot a closing parenthesis, you missed a semicolon, you spelled a command wrong.
And computers do not have the capacity for inference. The textbook points out that if a tourist comes up to you on the street and says, "How the geet to store do I?" the syntax of that English sentence is a complete disaster.
Right, it's garbage.
But as a human, using context clues and intuition, you know they are asking for directions to the store. You can easily parse the flawed syntax.
A computer cannot and will not do that. If your syntax isn't flawlessly aligned with the language rules, the compiler or interpreter just throws up an error message and refuses to proceed. It simply stops.
That sounds infuriating for beginners.
It is. However, as frustrating as syntax errors are for beginners, they are actually the easiest problems to solve. The compiler will literally point to the exact mistake and say, "Error on line 42, missing semicolon."
It hands you the solution.
It really does. So if syntax errors are the easy part, the true terror of programming lies in the logical error, or what is sometimes called a semantic error.
Because a computer will happily bake a gasoline cake if you tell it to.
Yes. This is the concept that truly separates amateurs from engineers. A logical error occurs when your code is syntactically flawless. All the grammar is correct. Every semicolon is in place.
Okay, so it looks perfect.
Yes. Because the syntax is perfect, the compiler gives you a green light, and the program runs without a single warning. But it produces a completely incorrect or disastrous result because the underlying context, sequence, or mathematics of your instructions are fundamentally flawed.
The textbook's cake analogy is legendary for explaining this. Imagine a recipe that reads, get a bowl, stir, add 2 eggs, add a gallon of gasoline, bake at 350 for 45 minutes, add 3 cups of flour.
Right. From a purely syntactical standpoint, those English instructions are perfect. Every sentence has a verb, a subject, and correct punctuation. If an English teacher graded the grammar, they would give it an A.
If a computer compiler checked it, it would compile perfectly.
It would. But the logic of execution is a complete nightmare. You are stirring an empty bowl, you are pouring highly flammable gasoline into a baking appliance, and you are adding raw flour to a finished, potentially exploding cake.
And the computer just doesn't care, just happily executes the steps.
Exactly. Or consider the text's other example. The dog chases the cat. Flawless syntax. But if you look at the window and the dog is actually chasing a tennis ball, the statement is logically false. The perfect grammar doesn't make it true.
Let's translate that into actual code. Suppose you write a payroll program to calculate weekly wages. The logic should be hours worked times hourly rate, but you make a typo and you hit the plus key instead of the asterisk.
A very common mistake.
So the code reads, hours worked plus hourly rate. If my employee works 40 hours at $20 an hour, they should get $800. But because I typed a plus sign, does the computer have any safety net? Does it have any way of looking at that and saying, wait a minute, $60 for a week's work seems logically wrong based on previous payrolls?
It has absolutely no idea. It is entirely blind to your original intent. A computer is perfectly, unfailingly obedient, and that is its most dangerous flaw.
Wow.
It will do exactly what you explicitly instruct it to do, not what you secretly meant for it to do. It sees the plus sign, it verifies that adding 2 numbers is syntactically legal, it adds 40 and 20, and it spits out a paycheck for $60.
And it will happily do that for 10,000 employees without ever raising a single alarm.
That is horrifying, honestly.
Yeah.
One wrong keystroke, no error messages, and the entire payroll system is ruined.
That is why logical errors keep developers awake at night. The compiler won't help you find them. You have to hunt them down yourself by rigorously testing the program, analyzing the output, and tracing your steps backward.
And because humans are incredibly prone to making logical errors, professional developers had to invent a foolproof system to catch these logic flaws before they ever touch a keyboard. You don't just open a blank document and start typing code.
Right, you follow the 7-step program development cycle.
Exactly. This cycle is the blueprint for creating stable software. Understanding these 7 steps is paramount, not just for the WGU exam, but for literally any career in IT.
Let's walk through it. Step 1 is understand the problem. And Farrell notes that this is surprisingly often the most difficult part of the entire cycle, because end users rarely actually know what they want.
They know they have a pain point, sure, but they don't know how to articulate the technical parameters of the solution. The text uses a classic human resources scenario. An HR director walks up to a programmer and says, "Hey, I need a program that prints a list of all employees who have been here for over 5 years so we can invite them to a special thank you dinner."
On the surface, that sounds like a 30-second job. You search the database. If hire date is greater than 5 years, print name, go get a cup of coffee.
But an experienced programmer hears that request and immediately sees a dozen logic traps.
Like what?
Well, do they want only currently active full-time employees? What about part-time staff? What about independent contractors?
Oh, right.
When you say 5 years, do you mean 5 continuous years? What if someone worked here for 3 years, quit to go to grad school, and has been back for 2 years? Do they get an invite?
That's a huge edge case.
And what data actually needs to be on the printout? Just names? Or do you need their home address to physically mail the invitation?
I can definitely see how a simple request spirals. But if I'm playing devil's advocate here in a modern corporate environment, is this really the programmer's job? Doesn't a company usually have business analysts or project managers whose entire job is to interrogate the HR director, figure out the leave of absence policy, and then hand the programmer a neat bulleted list of requirements? Why is the coder playing detective?
In a massive Fortune 500 company, yes, you will have layers of business analysts doing requirement gathering. But the reality is, even the absolute best BA will miss edge cases. And because the programmer is the one ultimately writing the strict, unyielding logic, they are the one who will hit the wall when they try to translate a vague requirement into binary code.
The buck stops with them.
Exactly. The text explicitly states that a good programmer must act as part counselor and part detective. If you don't fully understand the problem in step 1, every subsequent step is just building a house on a cracked foundation.
Okay, so once you've successfully interrogated the user and nailed down the exact parameters, you move to step 2, which is plan the logic. This is where you map out the sequence of events before you write a single line of actual syntax.
This is the heart of programming right here. You use tools like algorithms, flowcharts, and pseudocode. The textbook also details specific frameworks like IPO charts, which stands for input, processing, and output tasks, and TOE charts.
Let's expand on that a bit. What does a TOE chart actually look like in practice?
TOE stands for tasks, objects, and events. It's particularly useful for graphical user interfaces. For example, if you are building a simple login screen, you map out the objects, say, a username text box, a password box, and a submit button.
Okay, those are the objects.
Right. The events are what the user does, like clicking the submit button. And the tasks are what the program must do in response, like verifying the password against a secure database. It forces you to account for every single interaction.
And during this planning phase, the text highlights the practice of desk checking.
Desk checking is vital. It is the process of walking through your logic on paper, manually, with sample data before you turn on the computer.
Wait, on paper.
Literally on a piece of paper. If we go back to our payroll example, you sit at your desk, you take a pen, you pretend hours equals 40 and rate equals 20. You manually read your own logic step by step. If your logic says hours plus rate, you do the math on paper, you get 60, and you immediately realize you have a catastrophic logic error before you've even opened a software environment.
You catch the gasoline in the cake while you're still writing the recipe. I love that. So once the logic is ironclad on paper, we hit step 3, code the program. Finally, we're translating that logic into the specific syntax of a language like Python or C++.
Which is immediately followed by step 4, translate the program into machine language. This is where you run your code through the compiler or interpreter we discussed earlier.
And this is inherently an iterative process, right? You compile it, the compiler screams at you about 3 missing semicolons and a misspelled word. You fix them, compile again, it finds another error. You repeat this loop until the code translates cleanly with 0 syntax errors.
Exactly. It's a feedback loop. Once you have a clean translation, you have an executable program, which brings you to step 5, test the program. The compiler proved your grammar is right. Now you have to prove your logic is right by running the actual program.
And testing isn't just about making sure it works when everything goes perfectly. You have to actively try to destroy your own creation.
Oh, you have to be ruthless. You cannot just test the happy path. You must test the edge cases.
Like what?
Like, what happens if a user inputs a negative number for their hours worked? What happens if a customer tries to order 9,999 items online? Does the system crash? Does it give away free inventory? You have to feed it bad data to ensure your logic can handle it gracefully.
That makes sense. Once it survives your attempts to break it, we move to step 6, put the program into production. And the text makes it clear this isn't just flipping a switch on a server somewhere. It's an entire conversion process.
Deployment is incredibly complex. Putting software into production might mean training hundreds of data entry clerks on a new interface. It might mean writing a secondary script to convert 10 years of old legacy database files into a new format just so the new program can read them. It takes massive coordination.
And the final phase, step 7, is maintain the program. Because software doesn't exist in a vacuum, the real world changes.
Tax rates change, requiring payroll updates. Operating systems update, requiring compatibility patches. Users demand new features. A program will easily spend 90% of its life cycle in the maintenance phase.
Wow, 90%. Now, connecting this 7-step cycle back to the WG Reddit students, they made a huge point about chapters 7, 8, and 9 of their Zybooks material. They stressed that you have to understand how these 7 steps map onto modern development methodologies, specifically Agile and Waterfall. Let's unpack the difference there, because understanding why these methodologies exist is crucial.
Sure, waterfall is the traditional historical approach. It gets its name because the process flows strictly downward, like a waterfall, through the 7 steps.
Meaning you can't go back up.
Exactly. You do 100% of the requirement gathering, then you do 100% of the logic planning, then 100% of the coding. You never move to the next step until the current one is entirely finished, and it is very difficult to go backward.
But the software industry realized in the 90s that waterfall has a fatal flaw, right? Because what happens if you spend 6 months planning and a year coding, and when you finally show the user the finished product in year 2, they say, oh, actually, the market changed. We don't need this anymore.
That was a massive industry-wide crisis. Waterfall assumes requirements never ever change, which is a total fallacy. So the industry pivoted to Agile methodologies. Agile takes that entire 7-step cycle and compresses it into a rapid, iterative loop called a sprint, which might only last 2 weeks.
So instead of building the whole car at once, you build a skateboard in 2 weeks.
That's a brilliant way to phrase it, yes. You plan, code, and test just the wheels. You show it to the user, they give feedback. The next sprint, you plan, code, and test a steering wheel. You are constantly cycling through the 7 steps for tiny incremental features, allowing you to adapt to changing requirements on the fly.
That sounds so much more efficient.
It is. Understanding this evolution from rigid waterfall to iterative agile is a massive component of modern programming literacy.
Okay, I want to zoom back into step 2 of the cycle, planning the logic. Because as we established, the logic is everything. But how do we visually represent this logic so we can desk check it? When programmers plan, they rely on tools that strip away the confusing syntax rules so they can focus purely on the sequence of events. And the 2 titans of logic planning are pseudocode and flowcharts.
Let's begin with pseudocode. The prefix pseudo means false or fake. So pseudocode is literally false code. It is an English-like representation of logical steps. It is incredibly flexible because it completely ignores the strict grammatical rules of a compiler.
You don't have to stress about curly braces or semicolons. You just use plain English verbs. You might write start, and on the next line, input customerage, then set discount equals 10, then output discount, then stop. It looks structurally similar to real code, but it's meant exclusively for human eyes.
And the WGU students on Reddit talked extensively about a specific educational flavor of pseudocode called Coral, which is used heavily in their course. It's designed to be a bridge between plain English and real code.
A lot of students get initially intimidated by Coral because it looks formal, but user Scary Gary on Reddit pointed out a great survival tactic. They said Coral is actually highly intuitive. If you just take a breath, stop panicking about syntax, and read it like a plain English sentence.
That's the secret. It is designed to strip away the complex, distracting punctuation of a language like C++, so you can focus entirely on what the data is doing. But while pseudocode is great for reading, some people are deeply visual learners, and for them, we have flowcharts.
Right, the flowchart is a pictorial representation of logic. You draw specific geometric shapes that contain your instructions, and you connect them with arrows to show the flow of execution. But you can't just use random doodles. The shapes have standardized meanings.
It is a universal language. Let's break down the symbology. If you want to represent an input or an output operation, getting data from a user or displaying it on a screen, you draw a parallelogram. So the instruction input customerage goes inside a slanted parallelogram.
What about processing? The actual CPU heavy lifting, like doing mathematics.
For processing, you use a standard rectangle. Anytime you are assigning a value to a variable or doing math, like set discount equals 10, it lives inside a rectangle.
And we have to mark the beginning and end of the program, right? The terminal points.
Yes, the start and stop points are represented by terminal symbols. The standard shape is often called a lozenge or a racetrack shape. It looks like a rectangle with rounded, semicircular ends. You write the word start in the top one and stop in the bottom one.
And finally, you connect all these shapes with arrows, named as flow lines, which dictate the exact path the computer will take. usually reading from top to bottom or left to right.
Exactly.
This reminds me of a concept that Reddit students hammered on. UML, the Unified Modeling Language.
Yeah.
How does UML tie into these flowcharts?
UML is essentially the industry standard evolution of basic flowcharting.
Yeah.
While a simple flowchart maps out a basic algorithm, UML provides a comprehensive, standardized set of diagrams to map out massive, complex software systems.
Oh, I see.
For example, in UML, you have class diagrams that don't just show flow, but visually represent the structure of the data objects in your system and how they relate to one another. The Reddit students emphasize UML because passing the exam requires you to understand these standardized visual blueprints. If you can read a UML diagram or a flowchart, you can understand the architecture of the system before you ever see a line of code.
Let's bring in a textbook analogy to cement this. Using pseudocode is like writing down a list of turn-by-turn directions to get to a restaurant. Turn left on Main Street, go 2 blocks, turn right on Elm. Using a flowchart or a UML diagram is like literally drawing a map with the streets and directional arrows. They both get you to the exact same destination. They just present the logical sequence differently.
That's a perfect encapsulation. And the Reddit students offer a very specific, tactical piece of advice for the exam regarding these visual maps. One user noted that you must practice your knowledge of flow diagrams by interpreting how variables are represented after the process.
What does that actually mean for a student sitting in front of a multiple-choice screen?
It means you won't just be asked to identify a parallelogram. You will be shown a complex flowchart, and you will have to manually trace the path of a variable through it. Remember, a variable is just a named memory location in RAM whose value can change.
Right.
So the exam question might show a flowchart that says x starts as 5. The flow line points to a rectangle that says x equals x plus 2. The flow line then points to another rectangle that says x equals x times 3.
So you have to mentally walk the path. Okay, x is 5, plus 2 makes it 7, times 3 makes it 21. The final output is 21.
Exactly. Memorizing the shapes is utterly useless if you cannot run the logic in your head and track the state of every variable at any given point on the map. You have to become the computer.
Now, tracing a path is relatively easy when the map is just a straight line. Input, process, output, done. But real-world programs are never a straight line. What happens when the road circles back on itself? This is where we encounter the programmer's greatest tool and potentially their most destructive weapon, the loop.
The straight-line programs we've discussed so far, like doubling a single number or calculating one paycheck, are practically pointless. If you only need to process one employee's paycheck, you don't write software. You use a pocket calculator. The entire value proposition of a computer program is its ability to perform a task millions of times in a row without getting tired or making a mistake.
Yeah, but we wouldn't write the code millions of times. If I have a database of 10,000 employees, I am not going to physically type input hours, multiply by rate, print check 10,000 times in my text editor.
That would defeat the entire purpose of automation. Instead, we construct a loop. A loop is simply the repetition of a series of steps. In a visual flowchart, you would draw an arrow from the bottom of your output statement, pointing all the way back up to the top, re-entering the flow right above the input statement.
So it's a circle.
The computer runs through the code, hits the bottom arrow, loops instantly back to the top, and executes the exact same instructions for the next employee in the database.
But there is a massive system-crashing danger inherent to drawing an arrow that points back on itself.
Right.
Because computers are blindly obedient. If you just draw an arrow pointing back to the top, the computer is going to follow that arrow over and over, forever. You have just described the dreaded infinite loop. It is a repeating flow of logic with absolutely no mechanism for termination. If you accidentally create an infinite loop, the program will just run as fast as the CPU allows, looping millions of times a second, forever.
Yikes.
It will consume all available processing power, tying up the operating system's resources until the machine locks up, crashes, or a human is forced to physically pull the power plug.
So we have to introduce a traffic cop into our flowchart. We have to tell the computer exactly when to stop looping, and we accomplish this using decisions.
Yes. In a flowchart, a decision is represented by a diamond symbol. The logic flow line enters the top of the diamond, and inside that diamond is a specific question. Based on the answer to that question, the flow lines split, exiting the diamond in different directions. And the textbook lays down an incredibly strict rule about computer decisions. They must be binary. They must have mutually exclusive answers, which usually take the form of yes or no, or true or false.
You absolutely cannot ask a computer an open-ended question. The text provides a brilliant example. If you put the question, "What day is your birthday?" Inside a decision diamond, the computer will freeze. It's a terrible logic question because there are 366 possible answers. A computer requires a binary path, so you must rephrase the logic too. Is your birthday June 24th?
Because then the flow can cleanly split.
Yeah.
If yes, follow the flow line to the print happy birthday rectangle. If no, follow the flow line back up to the start of the loop.
Precisely. So to prevent our program from infinitely looping, we place a decision diamond in the path. But what question do we ask it to make it stop? We use a predetermined value called a sentinel value, or a dummy value.
A sentinel, like a guard standing watch at a gate. Let's say we are writing a simple program where a user types in numbers to be doubled. We might tell the user, enter the number 0 when you want to quit. Inside our loop, our decision diamond asks, is the number inputted exactly equal to 0?
And if the answer is no, it means it's valid data. The program doubles it, prints it, and loops back. If the answer is yes, the sentinel has been triggered, the program breaks out of the loop and follows a flow line directly to the stop terminal symbol.
Okay, that sentinel trick works perfectly for a small script. But what if we are processing a massive corporate database, say a file containing 1 million bank account balances? You cannot use 0 as a sentinel value to stop the program, because a bank balance of exactly $0 is a very real, very possible data point.
Right, someone to be broke.
Yeah, exactly. You can't use negative numbers. You can't use 999. Any number could be a valid account balance.
That is a fundamental logic problem that plagued early programmers. How do you signal the end of data when any data could be valid? The solution implemented by modern operating systems and programming languages is the E of marker, which stands for end of file.
What exactly is that?
It's an invisible system-level code automatically placed at the very end of every data file by the operating system itself. It is distinct from standard text or numbers. So instead of checking for a sentinel number, your decision diamond simply asks the system, have we reached the E of marker?
Oh, that's clever.
If yes, the file is empty, stop the program. If no, grab the next bank balance and keep processing.
That is incredibly elegant. Now, I want to jump in with a very practical exam-focused question here. On the Reddit threads, multiple students brought up a specific mathematical concept called the modulo operator. They warned that it appeared on the WGU test several times. How does a math concept like modulo fit into these decision diamonds we were talking about?
That is an excellent connection. The modulo operator, which is usually represented by the percent sign in source code, is a mathematical operation that gives you the remainder of a division problem.
Okay, remainder.
Let's do the math on air. If you evaluate 5 divided by 2, the answer is 2, with a remainder of 1. Therefore, 5 modulo 2 equals 1. If you do 7 modulo 3, 3 goes into 7 twice, making 6, with 1 left over. So 7 modulo 3 is 1.
Okay, I remember remainders from elementary school math, but
Yeah.
why is that useful for a computer?
Because modulo is the ultimate tool for creating binary yes or no questions out of complex data. The most famous and common use case is determining whether a number is even or odd. Suppose you want a loop to apply a specific discount only to even-numbered customer IDs. Your decision diamond can use the modulo operator. The logic asks, is customer ID modulo 2 exactly equal to 0?
Because by the very definition of mathematics, any even number divided by 2 has a remainder of 0. 10 modulo 2 is 0. 400 modulo 2 is 0.
Exactly. So if the answer to that modulo question is yes, the computer definitively knows the number is even, and it routes the logic to the discount process. If the answer is no, meaning the remainder is 1, the number is odd, and it bypasses the discount. You have just used simple math to force a complex data set into a perfect binary decision path.
That makes total sense. And it perfectly explains why the Reddit users aggressively advise bringing a calculator to the exam. You have to be able to manually figure out those remainders quickly when you are desk-checking the logic of a flowchart on the test.
Absolutely.
Okay, so we have mapped our flowchart, our loops are secured with decision diamonds, our modulo math is correct, and our logic is flawless. It is time to actually type this code out. But where do we type it? That brings us to the environments where code is born. Text editors versus IDEs.
When you transition from planning logic on paper to writing actual source code, you need a software environment to capture your keystrokes. The textbook delineates 2 main categories of these environments. Let's start with the simplest, text editors.
We're talking about programs like Microsoft Notepad on Windows, or TextEdit on a Mac, or Nano on Linux.
Exactly. These are incredibly simple, utterly bare-bones, lightweight environments used to create basic text files. They do nothing but record the characters you type. If you write a basic C# script to double a number in Notepad and save it, the resulting file is microscopic. It might only take up about 314 bytes of disk space.
But if I open up an IDE, an integrated development environment like Microsoft Visual Studio or Eclipse, and I type the exact same C# script, the textbook notes that the resulting project folder will take up over 49,000 bytes. It's massively larger. What is the IDE doing behind the scenes to inflate the size so drastically?
Well, an IDE is not just a blank piece of paper. It is a massive, heavy-duty suite of engineering tools integrated into one program. When you type in an IDE, it provides real-time features. It color codes your text, making keywords blue and variables green, so the structure is visually obvious.
That sounds helpful.
It is. It provides real-time syntax error highlighting, acting like a squiggly red spell checker for your code. It features automatic statement completion, predicting what you are going to type next.
And most importantly, it has built-in debugging tools, right?
Yes. A good IDE allows you to execute your code one single line at a time, pausing the execution so you can physically look at the current value of every variable in memory. It is the ultimate tool for hunting down those terrifying logical errors we discussed. But all of those graphical interfaces, syntax dictionaries, and debugging tools add massive computational overhead.
Okay, I have to push back on this comparison because
No.
it feels a bit archaic. We're living in an era where a basic consumer laptop has 16 gigabytes of RAM and a terabyte of storage. Hard drive space is laughably cheap right now.
That's true.
Why do I care about a 39 kilobyte difference? Why would any professional programmer on Earth ever use a bare-bones 314-byte notepad file? Why wouldn't everyone just use a feature-rich IDE 100% of the time? Is there actually a point to text editors today?
That is a very fair challenge, and for modern enterprise software development like building the next major banking app or video game, you are absolutely right. You will always use a heavy-duty IDE. The benefits massively outweigh the storage cost. But there are very specific, highly critical scenarios where lightweight text editors are non-negotiable.
Okay, give me an example where an IDE would fail.
Imagine you are a system administrator, it's 2 a.m., and a massive web server located in a data center halfway across the country goes down. You have to securely log into that remote Linux server via SSH, a secure shell. You are operating over a command line network connection.
Right.
You do not have a graphical interface. You cannot load a 4 GB installation of Visual Studio across a text-based network pipe just to change one line of configuration code. You use a terminal text editor like Vim or Nano to open the file, fix the typo, and restart the server in seconds.
Okay, that makes sense. The environment dictates the tool.
Also, consider embedded systems. If you are writing a script that runs on the microchip inside a smart refrigerator or a car engine, you have incredibly constrained memory limits. You cannot afford the bloat of an IDE project file. Furthermore, languages like Python, Perl, or Lua are specifically designed as lightweight scripting languages. Sometimes the sheer boot-up time and project configuration weight of an IDE slows down the agility of writing a quick 10-line script.
Different tools for different jobs.
Mm.
And speaking of different interfaces, the text also makes a necessary distinction regarding user environments, the command line versus the GUI.
Yes, and this is about how the end user, not the programmer, interacts with the final software. A command line interface, or CLI, is entirely text-based. You open a black terminal window, type a specific command, hit enter, and text comes back.
It's what computing looked like in the 1980s.
Precisely. A GUI, or graphical user interface, is the modern paradigm we are all accustomed to. It has windows, colorful buttons, drop-down menus, and mouse pointers. But the crucial conceptual takeaway for a student of programming logic is this. The underlying logic of the program is completely agnostic to the interface.
Meaning the flowchart doesn't change.
Exactly. The logic required to calculate a paycheck, the variables, the multiplication, the decisions, the loops, remains absolutely identical regardless of what the user sees. The math is the same whether the user clicks a beautiful gradient-shaded graphical button that says calculate, or whether they type the command calc_pay in a stark black terminal window. The GUI is just the paint on the house. The structural framing is the logic.
Okay, so we have laid down a massive foundation today. We've covered the hardware interactions, the translation gap, the unforgiving nature of logical errors, the 7-step cycle, the visual planning with flowcharts and UML, the intricate math of loops and decisions, and the software environments.
It's a lot of theory.
It is. Understanding all of this theory in a calm environment is one thing, but synthesizing it and applying it under the immense psychological pressure of a ticking certification exam clock is a different beast entirely. Let's dig into the survival tactics from the Reddit students who are currently fighting their way through WGU D278.
This is where the theory hits reality. When you look at the WGU Reddit threads, you find a fascinating, highly polarizing debate about the official course material, which is provided through a platform called Zybooks.
Yeah, user significant underscore bed 1645 was quite vocal. They complained that the Zybooks material was bloated with extra fluff and tedious participation activities that felt like a huge waste of time. They just wanted the core concepts so they could pass the test.
And if you already have 3 years of IT experience and you just need the credential, that approach might work. But another user, Tierfiend, offered a brilliant counter perspective. They argued that if you have never programmed before, if this is truly your first exposure to coding logic, working through every single tedious activity in the Zybook is not a waste of time. It is absolutely vital.
Because it builds muscle memory.
Exactly. Programming is a way of thinking. You cannot learn a new way of thinking by just skimming a summary. You have to put your hands on the keyboard and trace the logic paths until it becomes second nature. Skipping the interactive activities as a beginner is a guaranteed recipe for failing the objective assessment.
The Reddit community was also very clear about where to focus your energy. Multiple students pointed out that chapters 7, 8, and 9 are the absolute core of the exam.
Those chapters deal heavily with the program development lifecycle, the agile versus waterfall methodologies we discussed, as well as the deep dive into algorithms. You must internalize how those conceptual frameworks operate.
And what about the actual physical act of taking the test? What are the on-the-ground strategies?
The single most repeated piece of practical advice is bring a basic physical whiteboard calculator. You are going to be tracing complex loops that require multiplication, division, and extensive modulo operations.
Right, and when the clock is ticking and your adrenaline is high, you do not want to fail a complex, multi-layered logic question just because you made a dumb arithmetic mistake doing long division in your head.
Exactly. The test isn't evaluating your ability to do mental math, it's evaluating your ability to trace the flowchart. Don't let a math error ruin a logic answer. Secondly, and this was stressed heavily by successful students, do not rush reading the questions. The exam is specifically intentionally designed to trip you up on the nuances of logic.
I thought user bigger underscore than you had a brilliant piece of advice. They said, rewrite the questions in a way that makes sense to you.
That is a phenomenal strategy. The questions often use dense, formal language to describe a logic path. If you miss a single not operator, or if you accidentally misread a variable name because it looks similar to another one, you will trace the entire flowchart backward and confidently select the wrong multiple-choice answer.
The exam is testing your ability to read with the same strict, unforgiving precision as a compiler checking for syntax errors.
It is rigorous, detail-oriented pattern recognition. And finally, we have to talk about the psychological aspect of this specific course because it breaks a lot of students. It is completely statistically normal to fail the final objective assessment, the OA, on your first attempt.
A user named Dismo92 offered some incredibly poignant encouragement regarding this. They wrote, "The goal is improving and learning, not perfection. If you never knew people passed it the first time and just assumed the amount of times you take it is the norm, then there would be no pressure."
That is a very mature approach to learning a difficult skill. The transition from creatively reading pseudocode on a relaxed Sunday afternoon to taking a rigid, heavily timed, multiple-choice exam about abstract logic is a massive, jarring shift for the brain. You have to give yourself the grace to fail, to analyze your failure, and to learn from it.
I love that mindset. Taking a coding exam is fundamentally similar to learning how to play a musical instrument. You can read all the sheet music you want. You can read the entire Zybooks text. You can memorize the theory of notes, scales, and time signatures. But eventually, you just have to sit down at the physical piano and hit the wrong keys until your brain finally connects the theory to the action. You are going to hit wrong keys. You're going to accidentally write infinite loops that crash your computer. You're going to fail a test. It is a necessary part of the process of becoming a programmer.
Embrace the friction. Every logic error you make and successfully debug makes your mental map stronger.
Absolutely. Okay, let's bring this all home. We have been on quite an expansive journey today. We started at the lowest possible level, examining the physical hardware, the volatile RAM, and the software instructions that bring the silicon to life.
We covered a lot of ground.
We really did. We explored the translation gap bridged by compilers and interpreters. We navigated the rigid world of syntax errors and the deceptive, destructive danger of logical errors. We walked through the 7-step program development cycle and the evolution from waterfall to agile. We visualized complex logic with pseudocode, flowcharts, and UML blueprints. We wrangled infinite loops using decision diamonds, sentinel values, and modulo math. We debated the merits of lightweight text editors versus massive IDEs. And finally, we armed you with the tactical and psychological strategies to conquer the exam.
It is a massive, overwhelming amount of foundational knowledge, but this is the absolute bedrock upon which all modern software development across every single industry on Earth is built.
But before we let you go, I want to leave you with a final forward-looking thought to mull over. Something that builds on everything we've discussed today, but looks to the future. We talked extensively about the 7-step program development cycle. And we noted that step 1, understanding the problem, and step 2, planning the logic, are historically the hardest, most human-centric parts of the cycle.
Yes, the programmer has to be a counselor, a detective, and an architect.
Right. Teasing out the invisible edge cases from the user and mapping the flowcharts requires deep human intuition and logic. But what happens to the 7-step cycle in the rapidly approaching age of artificial intelligence?
Oh, that's a big question.
We are seeing the rise of large language models that can generate code. If an AI system can instantly write perfect, syntax error-free Python or C# code the very millisecond you ask it to, will the human programmer's only job become step 1 and step 2?
It's entirely possible.
Will our entire profession transition away from writing actual code? Will we just do the flowcharting, the logic planning, and the interrogation of the user to find out what they really want and then hand that UML diagram to an AI to generate the executable? Are we moving away from an era of coders who type syntax into an era of pure logic planners?
That is arguably the defining question for the next generation of IT professionals. If the AI is handling the syntax and the translation, then understanding the pure logic, exactly as we deconstructed it today, will become the single most valuable skill a human being can possess in the tech industry.
Exactly. So maybe learning all this theory isn't so much like learning an alien language after all. Maybe it's just learning how to think with absolute, unyielding clarity. Thank you so much for joining us on this deep dive into the foundations of programming logic. Keep studying, keep tracing those flowcharts, remember your modulo math, and we will see you next time.